Hello viewers, welcome to our series on three-dimensional geometry. So far you have understood how to form equation of a line in space, how to form equation of plane and a few other very significant results about lines and planes. Today we are going to be looking at the condition for two lines to lie on the same plane. When do we say two lines are coplanar? Let us start with an understanding of two lines, equations given, what do we know about them? Suppose I have line L1 and L2 given to us with their equations, vector r is equal to vector a1 plus lambda times b1 vector and L2 defined as r vector equal to a2 vector plus mu times b2 vector. So, if I have a line L1 equation given, what I do know about that line is that it is passing through the point A with position vector a1 and is along a vector b1. Similarly, L2 equation given to us means that the line is passing through the point B with position vector a2 and is along a vector which is say b2 vector. From the basic vector chapter and the conditions about the cross product, we know that the vector b1 cross b2 is always perpendicular to the two vectors b1 and b2 and hence to the plane containing the vector b1 and vector b2. Knowing that the line L1 passes through A, line L2 passes through B, if I can show that the vector AB, which is nothing but A2 minus A1 vector, is perpendicular to B1 cross B2. Will that then let us decide, conclude that the lines are going to be coplanar, because the vector B1 cross B2, which is perpendicular to B1 and B2, is also now perpendicular to the vector AB, and therefore, the two lines, that is L1 and L2, must be in the same plane. And that exactly is the condition for coplanarity of two lines, that is vector A2 minus vector A1 dot B1 cross B2 equal to 0 would allow us imply that the two lines are coplanar. In Cartesian, the same condition translates to the determinant x2 minus x1, y2 minus y1, z2 minus z1, second row a1, b1, c1, third row a2, b2, c2. If this determinant is 0, then the lines are coplanar, where x1, y1, z1 were the coordinates of the point A, x2, y2, z2 coordinates of point B, and the vector b1 has direction ratios a1, b1, c1 and vector b2 has direction ratios a2, b2, c2. It is a simple to use property that comes in handy. If you look at our problem here, that is exactly what it requires. We want to prove that the lines vector r equal to minus I cap minus 3j cap minus 5k cap plus lambda times 3I cap plus 5j cap plus 7k cap and the vector r equal to 2I cap plus 4j cap plus 6k cap plus mu times I cap plus 4j cap plus 7k cap are coplanar. And not only that, the question also asks you to find equation of the plane containing these lines. So, a little extension of the problem is also added. So, how do we check whether the lines are coplanar? As we discussed just now, find the vector AB, which is A2 minus A1 and consider B1 cross B2. So, if I can show that vector A2 minus A1 dot B1 cross B2 is 0, the lines are coplanar. In this this case, we have the vector AB, which is A2 minus A1, coming out to be same as 3i plus 7j plus 11k cap. Let us see what B1 cross B2 looks like. Using again the determinant form, I get B1 cross B2 to be a vector same as 7i cap minus 14j cap plus 7k cap. What do you have to do now? Verify that AB is perpendicular to B1 cross B2. So, find the dot product, and as you can see here, the dot product turns out to be 0. That implies that the lines are coplanar. But how do we find now the equation of the plane containing these lines? Remember that to form equation of the plane, the two things that you need the most, one of them is the normal to the required plane. Isn't B1 cross B2 perpendicular to the plane containing the two lines? And therefore, B1 cross B2 gives us the normal to the required plane, which we have already calculated. And so, the normal to the plane is 7i cap minus 14j cap plus 7k cap. What else I need to form equation of the plane is the point. Now, the line lie on this plane, and therefore, the point of the line, the known point of the line becomes the known point of the plane, and therefore, the point minus I cap minus 3j cap minus 5k cap lie on the plane, and therefore, using the form r minus a dot n equal to 0, we get the equation of the plane containing the lines as r dot 7i cap minus 14j cap plus 7k cap equal to 0. Isn't that simple? Very algorithmic. You don't have to think too much, but the basic understanding remains in knowing that B1 cross B2 is always a vector perpendicular to the plane containing the vectors B1 and vector B2. That's a very neat result that does come in handy in number of places. We have here another question for you, and the question says, show that the line given by the equation vector r is equal to I cap plus j cap plus lambda times 2i cap plus j cap plus 4k cap lies in the plane r dot I cap plus 2j cap minus k cap equal to 3. Now, the line lies in the plane. The plane is given with a certain normal, which has the direction ratios as 1, 2 and minus 1. Now, for the line to lie on the plane, is it enough to show that the normal is perpendicular to the line? What if the line is parallel to the plane? The condition is still satisfied, but the line does not lie on the plane. So, for the line to lie on the plane, along with showing that the normal is perpendicular to the line, I must show that the point which lies on the line also is a point of the plane. Therefore, if I can show that the point A satisfies the equation of the plane and the vector n is perpendicular to the vector B, which defines the direction of the line, then our job is done. Here we have the vector n, that is normal to the plane as I cap plus 2j cap minus k cap, vector B, which gives us the direction of the line as 2i cap plus j cap plus 4k cap. Simple dot product gives us 0, and therefore, the line is perpendicular to the normal, but it could be away from the plane, it could be parallel to the plane. So, further, if I take the point I plus j cap, which is lying on the line, and replace it in the equation of the plane, I get again the dot product turning out to be 3. That confirms that the point of the line is also a point of the plane, and therefore, the given line lies in the plane. I would like now you to think of an alternative. Is there another neat alternative to this problem? How do I show that the line lies in the plane? Exactly, if every point of the line lies in the plane, then the line has to be contained in the plane. If you look at the equation of the plane and the line, you will realize that if I replace the vector r in the plane with the vector r, which gives us the general coordinates of any point on the line, then if the equation is satisfied, our job is done. So, here if I replace r in the equation of the plane with the r vector of the line, I get the dot product turning out to be 3. Irrespective of lambda, the position vector of any point of the line satisfies the equation of the plane, and therefore, the given line lies in the given plane. So, that is a one step alternative to our problem. Let us take a look at another question, which is an interesting one, slightly away from the normal usual form of the questions that you have looked at in our series. The problem says a variable plane which remains at a constant distance 3p from the origin cuts the coordinate axis at A, B and C. Show that the locus of the centroid of triangle ABC is given by this equation. This expression is nothing but reading it as a 1 by x square plus 1 by y square plus 1 by z squared is equal to 1 by p squared. Now, how do we come across such an expression? Start with an understanding that a variable plane is cutting the 3 axes at the points A, B and C. So, if I take the point A to be A00, because that is the point on the x axis, small a, lowercase a is a varying quantity, it is not fixed. Similarly, the point B, where the plane cuts the y axis, can be taken to be 0, b, 0. C point has the coordinates as 0, 0, c, where small a, b and c are all varying quantities. This is just one position of that plane. Once I understand the plane is cutting the intercepts A, B and C, then using the intercept form of the equation of the plane, I have the equation as x by A plus y by B plus z by C is equal to 1. Also, we have a small result which suggests that the perpendicular distance of a given point, say x1, y1, z1 from a given plane ax plus by plus cz plus d is given as the absolute value of the quantity ax1 plus by1 plus cz1 plus d by under root of a squared plus b squared plus c squared. Using this result and following the condition given that origin is at a distance 3p. So, 0, 0, 0 is at a distance 3p from the plane x by a plus y by b plus z by c equal to 1, and therefore, 3p must be equal to absolute value of minus 1 by under root of 1 by a square plus 1 by b square plus 1 by c square. So, if you apply the formula to the plane x by a plus y by b plus z by c minus 1 equal to 0 and replace x1, y1, z1 with origin 0, 0, 0, you get this result. From here, if I just square both the sides and take the reciprocal, I get 1 by 9 p square is equal to 1 by a squared plus 1 by b square plus 1 by c square. So, how do we get the centroid of the triangle in the picture? If I take the centroid of the triangle to be x, y, z, then by the basic coordinate geometry result and the of course application of the section formula, the centroid should be a by 3, b by 3 and a c by 3. Therefore, x must be a by 3, y b by 3 and z must be c by 3. So, a, b and c are nothing but 3x, 3y and 3z. So, if I know the values of a, b and c as 3x, 3y, 3z and I am interested in finding the locus of the centroid, that is a condition on x, y and z. So, what I can simply do is replace, substitute the value of a, b and c in the condition 1 by 9 p square equal to 1 by a square plus 1 by b square plus 1 by c square. So, if you replace a, b and c with 3x, 3y and 3z respectively, you get the required condition, that is the locus of the centroid as x to the power minus 2 plus y to the power minus 2 plus z to the power minus 2 equal to p to the power minus 2. With this question, we conclude our series on three-dimensional geometry, where we learned about line and plane. Varied forms of equations of line and plane are definitely important. Simple logical understanding is used to form the equations. So, do take up more problems from your textbook and hopefully you will not have any problem dealing with any one of them anymore. All the best to all of you.